Okay, so we have now. Fine. So we can discuss the projects in the class later, but now for now we are doing deep learning, and we have to continue from there. Where we left, we talked about PyTorch, how PyTorch can be used, and Tensor also we have seen. We will be using Tensor today, TensorFlow, and same examples and see how it works in the little more theory to it. So I've already added a bit what we are going to do. Deep learning using TensorFlow. We have the APIs, different APIs we have. So we have deep learning libraries and all. And here we have a GPU which is required for Tensor. It does not. It won't work on CPU. CPU is your simple system. Uh, your laptop or your computers, whatever you're using, desktop or whatever. And GPU is parallel processing, having a graphic card. In your case, if you want to change that, I'll change the runtime to GPU. Uh, I can change the runtime from here, runtime type, and here it is none. So I'll make it GPU. You have two options, GPU or TPU. We would be using GPU. Okay, so and just let the options be default. You don't have to select anything. Just say okay. I have to do it because if I don't, then whatever I have done, then I'll have to run again. So I've done it now, and deep learning using TensorFlow, a bit of it is there. Then APIs we have to use. Okay, and the module we are going to use is Keras that we have used earlier also. A bit about Keras also. I'm just putting here. And I'll be putting some links also. So Keras is simple, flexible, and powerful. And why it is powerful, you'll see that YouTube, Wamo, NASA, they're using Keras. Okay. It's very simple, flexible, and simple. Just have to call modules and do that. Deep learning is no rocket science. Okay, so first thing is data. Data is important for any machine learning, deep learning, or any activity. You require data. So load data. Okay, so we can use the data from the repository which we already have with the modules. Like with Keras also we have the data and what we did earlier also. So you can load that, and I have already given you the link, I believe. You can see that the MNIST dataset is an image dataset of numbers. So you can load that. Normally, these are arranged in folders. So you have the training image and training test images. These are the folders, and then we have the labels also. So what you are reading, it loads from there, and it just stores in the variables I've given. So mns.load data inbuilt module, which function we are calling. So it will help me load my data. So let's load it. It'll take little time. Uh, let's wait for the data to be loaded, and then we can go ahead. So we have to. First thing is data. This data is actually your image is a matrix. Okay, it is a matrix form, and the data is in numbers only, integers only. But you have to actually normalize your data so that your data is actually aligned with each other. And when I say that, actually, what happens in deep learning or machine learning or cognitive learning or whatever learning we are doing, when we take a data, then it has to be of the same shape, right? So you cannot have different shapes just like that. Otherwise, you'll have to reshape them to similar shape. Otherwise, actually, it won't work. It won't compile. The reason is if the arrays, these matrices, data, yeah, this the data is in form of matrices only, arrays only, multidimensional or you can say n-dimensional arrays. So if they are not of the same size or same shape rather, then it won't fit. You can see that there would be gaps and all. You can imagine yourself that there would be if one is having 10 rows, the other one is having 20 rows, and the next is having, let's say, 5 rows, then it is just like a staircase you are doing. So, and the size don't match, and the code won't work. Your algorithms won't work on unstructured data, so or not of the same shape. You can say that. Okay, so the shape has to be same. So in a benchmark data set, we don't have to worry about it because the benchmark data sets like MNIST data set, it is more or less of the same size, but still we can actually check, and we can confirm, and we can flatten, and we can normalize also. We can reshape also, so that every image or every array has the same size. So these are arrays or matrices, you can say, since they're multi-dimensional arrays, so we can say that matrices. Okay. So let's see what we will do with this data set, and how we are going to manipulate that. First, we have to plot it like we did earlier also. So we will be just using matplot. I'll just tell you what all we are using, the variables we are using here. Uh, number of rows, basically 20, image train image, and labels. We are just taking 2020 so that we can print them 0 to 20. You can increase or decrease the size, number of rows and number of columns. This is for the figure actually. Number of rows, number of columns, and number of images we are taking. Okay. So this is actually for the display purpose only on the screen. You can see that it is used, this also, figure and axis, plot to subplot. Now subplot gives me the area where it has to divide your canvas and display the images. Okay, this one, the output canvas, has to be divided in the number of rows, columns, and figure size you have given. That how much size you want, 1.5 by number of columns, 2 by 2 into number of columns. We can change it and see also. I'll just run it and show you. So num is 20. So from 0 to 20 it is going to run. One by one we are reading axis, and we are just plotting them and showing them. So it is there in images, so you can read it from here. You can see that. This is just defining the axis. This is ax dot show image I, cmap gray image, we are gray scale we are using, and title we have put, and that's all. So you can see that. Labels automatically whatever is stored in the images that is displayed, and I can show you here, and if I change it to 2 happens. You can see more I can display. I got more rows to display now. So I can increase the 20, and here what we are having is 1, 2, 3, 4, 5, 1, 2, 3, 4. That is, we have all the 20 images here. So what are whatever images we have written, sorry, read, are displayed here. So from the figure size, you can manage the image display. Okay, this is what is done here. So MNIST dataset is in image dataset. You can see all the numbers, handwritten numbers, and we are just displaying that for now. It was just a display, nothing else. Now we have to do we have to check the size of the image. So we have train image, I believe. Let me get that. Yeah, train images dot shape. Let's put it here. Dot shape like this, or you can put it in a print. It won't matter. Single line will execute 6,000. 6,000, 60,000. 1, 2, 3, 4, 5, 60,000, 28 by 28. Okay, that is the pixels. Test. You'll have the test. There are a lot of images here. 28 by 28. 60,000 images we have. The test images. I think it is images only. So if it is not, then I'll have to change that. This is 10,000. Yeah, 20. So it is divided actually. Test training and testing 60, and that means there would be like 70,000 images of size 28 by 28. It's not big. These images are not very big. If you take big images, then there is always a possibility of collab crashing. And as I think it did for some Paranjal or some Pranjal or something, I don't remember actually. Someone Pranjal, it was Pranjal, I think, who told me that his collab crashed. It is possible that collab may crash. If it crashes, just restart it, run it again, and your codes would run. These we only use very small data sets, so it should not crash. But if you keep on adding the notebooks and keep on running them, then the memory issue could be there. This is not a paid version we are using. We are using a free version, so there would be some issues as far as memory is concerned. So if your memory get exhausted, then you may land up with some errors. So just shut down your system or restart your collab, your browser, clean the cache, and just try to run it again. Your code should run. But if it is a huge data set, then it will be a problem. This is a small data set, although the images are almost 70,000 images. But the size is just 28 by 28, so it wouldn't be taking more than 2 or 3 kilobytes KB one image. Okay, so it won't be much, right? So that should not create an issue, and you will work on it easily. So you can work on it easily. Okay, and let's have the labels also. We'll see the shape of the labels. Train label and test labels will be the same. 60,000. There won't be any. These are just numbers, so it won't be like on matrix form. Train and test labels also. Let's check that also. Very simple shape command. Have the test labels. This is 10,000. Okay, so 60,000, 10,000 is 70,000 total. Shape you can see. So it is important actually to check the shape of your data. It's not that it is because of image I'm checking the shape. Otherwise, also I would have checked the shape, the size, because it matters. It may give me errors in the end, or it may be giving me errors just right the moment I start, but it sometimes it happens that it may give me some errors later also. But anyway, so for now the shapes are okay, and because it's a benchmark data set, so now what we have to do is we have to import the models and the layers. Layers are very important. So I'll just put some query about that before I put anything. So what all is required. So layers are the core building blocks, and layers are like your sieve, chandi jo hoti hai, they are like that. So they filter out your data. They even fetch the relevant features from your data, and then it just pass on. So one layer, let's say if it is a uh, dense layer, one that is closely connected layer, and the second layer would be a softmax layer, and let's say 10 away softmax layer, which means it will return an array of 10 probability score, that is summing it all sums up to 1. Okay, so each that probability, that current data belongs to one of the 10 digits. Like suppose we have numbers 1 to 10, so each of the image would be belonging to either 1, 2, 3, 4, 5. That is of the 10, it would be belonging to some of the labels. So you can say that 10 is the probability score, that is the labels we are giving. The images, let's say there are 10 classes of the images, suppose. So out of the 10 classes, whatever image I get is one of them, right? So this you have the first it would be your dense layer, and then would be your softmax. That is normally the last layer, as I think I told you earlier also. Normally the last layer is a softmax layer. Is now what we need more is your loss function optimizer and the matrix. Okay, so how the function the your network is going to handle the loss, that we have to define in you have different loss functions also, like cross entropy and all. So you can use that, and we can have a look at what all loss functions we can have. Then we have an optimizer. It is Adam normally, or you can use any other ReLU or something like that. There are many optimizers also, inverse optimizers. They're all matrices, sorry, mathematical formulations. So, uh, so the network optimizer helps the network to update itself depending on the loss. So if there's a loss coming, then it will optimize it and will try to minimize the loss. Okay. Then we have the matrix to monitor during the training and testing session. During training is like testing matrices has to monitor. That is here only uh, we are only worried about the accuracy, how the accuracy is going on, and you have to say check that whether it is classified correctly or not. So matters will be that. So we have three things here: loss function, optimizer, and matrices for any data set. Okay, it can be image data set or it can be otherwise also. So now let's have from Kira's, where did I type? From Kira's import model, and just paste it. Taking models. Yeah. Okay. Sorry, it is from. Okay, from Kira's import layers. We need layers and a model. Now we need a network. The model, we can say model dot, normally we take sequential. So we're going to take that, the different models. Models dot sequential should be okay. Is it okay now? Yeah, it's okay. Now we have to add the layer. That is first layer we are going to have as a dense layer. Here we are giving a 512 size, that is neurons. Activation is ReLU. Activation function is required, and input shape is 28 by 28. That we have already seen. Okay, so we can use like this. You can decrease there 512. It can be anything. So we have to give that. Now this is the first layer, and then we have one more layer, that is your softmax layer. And again, as I have written earlier also, that it has to take 10 digit classes, 10 probability scores we are having here. So we are giving 10 there out of 10. What is the probability. So here we have, I think, digits are 1 to 9 or 0 to 9. That is 10 digits we have. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have given 10 here. This is to manage the images. Okay, so it doesn't matter what I give here. Now I can run it and see if my model is okay. If there is no syntax error, it will compile. Yeah, it's fine. Now you have to compile that. Is to run, we need to compile it. So we have three things, as I said. In when we compile the network, we need an optimizer. Uh, Here we have used RMS prop. Then loss is categorical cross entropy that what I was telling, and matrix is always accuracy. Matrix you don't have to worry. Loss may be different, so loss functions and your optimizer functions could be dif- different. So we are using here optimizer RMS prop, categorical cross entropy. If it is categorized, the data is in categories, then we use categorical cross entropy. There are many more. And I think I have the link I'll share with you. I think I had somewhere. Let me check. It's okay. I'll give you. I think I have it. Yeah. I'll just put the loss function first. And see, here we are having the loss function. So we have the binary cross entropy, categorical cross entropy, and sparse categorical cross entropy. Okay, so we have written here what it is all about. Binary cross is, binary 0, 1. So category wise, again, 0, 1 we are talking about. So use a loss function for binary classification. We use binary cross entropy. If the data is in binary form. Okay, and categorical cross entropy use a loss function of multiple class classification. Okay, where we have more than two or more than two output labels. The output label is assigned one hot category encoding value in the form of zeros and one. It is called one hot category encoding. Okay, and the labels are given 0 and 1. Output label, if present in integer form, is converted into categorical encoding using keywords, utility, categorical methods. We can convert it. Okay, so labels can be converted, labels can be given zeros and ones, something like that. Then the sparse category cross entropy, categorical cross entropy. That's the labeling here starts from 0, 1, 2, 3, and so on. And the details are there. You can have a look at what loss function does and what all options we have with the loss function. Okay, so let's work on it first. So we need a numpy first, and we have to, as I said, we have to reshape everything. We have to make sure that every image is in the right shape. So we will just reshape it, although it is same, but still, just in case if any of the image is missing the shape, then it will be reshaped. So train images is equal to train images dot reshape. The command is just reshape, and the 60,000 28 by 28. That is, every image has to be in shape of 28 by 28. All the 60,000 images have to be in 28 by 28 shape. Now I have actually to make sure that they are all float 32. This is what goes wrong when we do image processing. We don't do this, and then we land into problems. So we have to actually make sure that every pixel, every data in my image should be of the same uh, data type. That is float 32. 255 is number of colors. So if it is an RGB image or a gray image, we are just dividing it by 255. So to make sure that all are of the same float value. So we call it normalization, and then same we will be doing with the test images also. Training and testing, we have normalized. Here it is 10,000 and training were 60,000. Now, a little more we have to work to normalize that. We have used expand dimensions, train images -1, test images -1 till the end. Actually, we're just converting that, and let's see the shape now. Let's see what we get. Shape of the training images. Training images shape 784, that is 288 by 28. It is now 60,784 by 1. Training image shape and train samples 60,000 and test samples are 10,000. So this dimension, expand dimension, has changed the shape now. Normal, the images actually, the data when we pass should be in linear form. Okay, so that is what expand shape is doing, because the other part is not in the shape of one. It, it is 10,000 by 28 by 28. The labels are single. So you just have to flatten the images. You flatten the images or expand the dimension, and just you have to create the labels now. So before training, the process, the data has to be reshaped into shape the network expects, and scaling it so that it all the values from 0 to 1, that is we have to scale it to 0 1. So the the images which we read, that is the training images, were in 60,000 28 by 28 of type unsigned integer 8. Okay, and the values were 0 to 255 interval. That is what I told you. The colors range from 0 to 255. And then we have to transform into flat 32 array, shape 60,000 by 28 by 28 with values between 0 and 1. Okay, so we are using categorical cross entropy. We have to do that. So that is what we have done. And now we have to put everything together. I can put it everything together. I can simply run the code. Okay, expansion we have already done. So now convert the class vector to class matrices. So we have to do this. Convert class vectors to binary class matrices. So Kira's is there, just telling me. Okay, I did not. I have not changed it actually. Is it X train and Y train? I have to explain that. So let me put everything together and just put the code together. And I'm not using the same names, so I'll have to change the names also. That's okay. It is giving errors. I don't know. It should not. From TensorFlow.keras import layers. From TensorFlow import keras. So we are using now TensorFlow. Earlier you can see that I was using only keras. Okay. But now from TensorFlow I am importing eras, and from TensorFlow.keras import layers. And the number of classes 10. Input shape is 28 by 28 by 1. That we have already given. Then testing, and then we are loading the data again and converting the same thing we are doing, but now we are using TensorFlow. Okay, and let me run it. It will give you the same results. as earlier. You can see that 28 by 28 shape we have. But now we have to convert into categorical matrices, class matrices, binary class, convert class vectors to binary class matrices using two categorical, because we are using categorical cross entropy. Okay, so we are just converting it. You can see the, if you want to see, you can print the data and see, but it will take a lot of space. Now, the model. We have the sequential model as we did earlier also, so we'll be putting here everything. So model is keywords.sequential, keywords.input shape is input shape, that is the shape we already have, 28 by 28. Now we have different layers here now. Convolution 2D, 32 points. Kernel size is 3 by 3. Activation is 0. Kernel size can differ, vary. Then we have the max pooling 2D. Then that is size is 2 by 2. Then convolution 2D again, 64. Kernel size is 3 by 3. Activation is again ReLU. And then max pooling 2D. Then again size is 2 by 2. This is the layer on which we are creating dense layers. Then we flatten it. Then we have a dropout of 0.5. That is, you just remove errors. Dropout, there is a layer, a filter layer basically, which clears the data. Then we have a dense layer, that is the last one, which we discussed earlier also, that it has to be softmax. So activation is softmax, and number of classes, whatever we get is the number of classes. We've already given number of classes, I think, to be 10. I think they are 10, something like this. Let me see. Oh, I close it. Okay. Yeah. So we have already given that number of classes 10. So you can have a look at the summary of the model. You can see that. So input shape, output shape, we have whatever we are given. The output shape is 26 by 26, 32, 13, 13, 32, and 11, 11, 64. Then we have 1600 and all. You can see that. Parameters. So the total parameters used is 34,826. Training parameters is 34,826. That is what the total parameters are. And there is nothing which is not trainable. So that is the summary it gives you. Loss function, I've already told you what loss function is. Now let's run it. It takes time, and you can see that. And let's show you. Batch size is 128, epochs is 15, that is number of repetitions. Then model would compile losses, categorical cross entropy, optimize it. Astem matrices again accuracy as always. Then model dot fit, extrain, y train, batch size. Then epochs, that is number of epochs, and batch size 128, and validation is split the data into 90, 20, 10. So let's run it. It will take little time. It will take little time. So they are only 15 and the size is small. So it won't take much time, but still it will take little time. So let's see. What, this won't take much time because the size of the data is not big. But when we train our data like 1 GB data or something like that, or 1 TB data, then it takes ages, and sometimes we have to wait for days or at least a day. You can see that the losses, you can see the accuracy, validation loss, and the validation accuracy. So you can see that it is increasing with each epoch, each iteration, each repetition. That is, you've sent the data through the layers, it works then again and again and again till all the epochs are met. So it will keep on filtering, keep on filtering, and then it gives you the output. That is the final output you get. So let's see what we get here. This is a very simple implementation, and we just have to find out the score we get. So model.evaluate, x test, y test, verbose is 0. Here we don't need any actually. Verbose is actually how the data is divided. So it makes sure that it is in equal division. Like if you have a binary data set of zeros and one, then it makes sure that equal amount of zeros and ones are there in the training and the testing set. So anyway, here we are using verbose is equal to 0. So score, we have to check the score what we got, and this is what we get. The testing loss is 0.02, and the test accuracy is 0.991. That is 99% accuracy. You can multiply by 100 and see how much we get. This is 99% accuracy, which is a very good accuracy. It is expected. It is expected. The reason is that the data set is already a benchmark data set. Plus, we have actually uh, flattened the images also, and we have reshaped, and we have made sure that they're all 432, and they fall in the range between 0 and 255 only. So we have done that also, and then we have made sure that images are 28 by 28 only. So that also we have done. We have expanded the dimension, the extreme right team -1, to make sure that they are 28 by 28 by 1. You can see how the images are done, and this is a very simple implementation of deep learning using convolution neural network. Okay, this is a convolution neural network. 2D, we have 3D also. These days we have 3D also. When we started, we had only one layer, 1D convolution. That's the simple convolution neural network we had. Now we have 2D and 3D also. 3D also, convolution 3D also is also there. So this is a mathematical formulation actually of a neural network. And if you want to go into the details, I can share it with you. But we have to see that what we have to implement. And I have shared the link for yeah, Kira's link for the losses. You can go to this API and check. You'll get everything about the labels and all, and the examples also. The same example may be there also, right? This is a very common example which is taken by everyone, because the implementation and everything is so simple that it can be shown easily. Okay, so it may be there. I normally take from the APIs, direct APIs only, references or the manuals only. So but you can use your own data also. It's not necessary that you use this data. You can always change the data, but you cannot load the data uh, here like we have loaded from MNIST. So all I have to do is you have to read an image folder that I can show you, and I was working on that only on a potato leaf project. So we can use the folders, and we can read from the folders, and it can actually convert it into training and testing. But we have to flatten and all, we have to do everything so that we can get the things into shape. I think I have that code with me. I can show you uh, how we can load. Let me first share this. Let me Save it on GitHub. Collab has some limitations as far as memory is concerned. So you can't use big data sets here. It is not a paid version, as I told you earlier also. You have to see that. Query is okay, important, but not that important. It is for your understanding only. I'll share it at Teams. Okay, I can put a link here. Right, and let me share it on our group also. Oh, it is not there. Let me give me 2 minutes. Simple implementations are there. LSTM is something which we use normally, but we can use convolution 2D also, or convolution simple, or convolution 3D also. Only there is a difference in the syntax, otherwise everything is same. You have to get the data, split the data into training set, testing set, and then compile the model and get the predictions. It's very simple. You don't do anything much there. But data is important. That is something you have to work on. And there is this. Okay. Right. So I have shared it with you. Okay. Right. There are a few pending things which you have to cover. So I've shared with you, and we have what 10, 11, 12, and 13 notebooks which have to be done. And let me stop the recording.